All right, what is today? October 1st, 2024. Today we are going to talk about lithium battery pack design with my class full of mostly senior MEs here at Purdue. Can you guys see this? Zoom, people on Zoom, can you tell me if the TV's visible enough? Like if I
Not
go to
really.
the, not really? Okay. Well, I guess I could share my screen as well. So how about that? Now you guys are able to see my screen. Yeah, is that like a choice of yours? You can look at my screen.
Yes.
Yes.
All right. Well, hopefully the screen record can look at my screen as well, and can hear me all right. So here we go. Let's talk a little bit about. Let's review what we learned in the last two classes about lithium batteries or batteries in general. Really, we know that there's three different battery formats: cylindrical, which is like these 18650s I have in my hand right here. There we go. We have prismatic, which is actually, if you, this is a module, so I shouldn't confuse you. Prismatic look like a module. They're easier to use, mostly used in DIY. You can see all the information I have on each here. And then pouch, which in my impression is the most raw form of lithium. That's the form that you get lithium polymer in. And lithium polymer is like the lithium of lithium. It's very powerful, very energy dense. But it also expands. You need to account for that mechanically. Anyway, so we're dealing with cylindrical today in our battery designs. The three different cylindrical type cells that we will talk about: 18650, 21700. Those are both lithium ion cells. And well, 4680 is new. I haven't seen one in person yet, but supposedly that's maybe what's going in Teslas right now in 2023, 24. If you see a 26650, that is a lithium iron phosphate. Lithium iron, hence the Fe, phosphate. These are lithium ion. And we all know that the first two numbers, the diameter and then in millimeters, so 26 millimeters diameter, 65 millimeters height. And then you've got different chemistries here, lead acid being the least energy dense and powerful compared to its volume and weight. Obviously, lithium iron phosphate, lithium ion, and lithium polymer is the most energy dense and power dense that they can come. And it only comes in pouch cells. Just for the recording, prove to me you guys know what series cells. If you stack series cells, you are adding what? Voltage. If you stack parallel cells, what are you adding? Yeah, amp hours, capacity, amp hour capacity. Nice. Okay, this is perfect. If you guys can see the camera, I'm going to throw out some examples here because we talk about individual cells. We talk about a module / brick, which is usually 1s blank p. For example, this one is 1, 2, this is 8p right here, 1s, 8p. And then a pack, which we're going to design, is fill in the blank s, fill in the blank p. It's whatever, 20s, 30p. And that's what we're going to design. State of health versus state of charge. State of charge is how much energy or capacity, electricity is left in your current charge until your battery is quote unquote out, 0% SOC. It's dead. It's out of charge. State of health is the long-term health of the battery, and it's measured by amp hours that were originally that it was originally able to produce divided, or excuse me, the amp hours that it can produce now divided by the amp hours that it was originally able to produce. And that's the state of health of your battery. And then finally, we all know that voltage is not an indicator of state of charge. You cannot determine how much charge you have left in your battery based on voltage. And this is why, because voltage, according to state of charge, is flat right here. So your 3.7, which we all know is the nominal voltage of a lithium battery cell, the 3.7 volts could be 80% state of charge, or it could be 20% state of charge. So you actually want to use other methods like Coulomb counting for determining range and state of charge. That's a whole different conversation that I can talk a lot about in terms of range estimation for EVs or state of charge for electronics. Anyway, but we're not talking about that today. Today we're talking about battery design. That wasn't what I wanted. Here we go. I'll go to the camera. So these are 18650s, right? And I'm gonna actually first off hand it out. I made these were real, they went in the hoverboard that I designed. And one on each side. And if you read this, you can see here it's lithium ion battery, 18650s, obviously, 5S2P, 5S2P, pretty confusing. Okay, 5S2P, so 5 series, 2 parallel, which means there's 10 cells in this right here. Okay, and it's 18.5 volts, which nominal, which we could have done the math on, 5 times 3.7. And then this is 6.4 amp hour, which that will tell you actually what cell it is, right? And, you know, we talked about that last class, but we'll get into it more. And then this was made in 2017. And actually, you can feel there's actually a battery management system on top of it. In fact, I'll actually pass this around because I disassembled this morning with a razor blade, which was how we evacuated one of the buildings here on campus 10 years ago. So I was very careful. And so you can see that this is the battery management system on top of the cells that are all tab welded with nickel sheets through here. So these are just, you know, blank 18650s. This is the, you know, what you would get if you were putting this into your system. And this is what it looks like, right? You've got your high current discharged cables. And then I also had a smaller cable coming off here that was a smaller digital, I think it was, yeah, just another pack voltage, but it was a smaller cable meant for digital readings or analog readings. But anyway, so let me pass this around so you guys can see this. You already seen 18650 stuff. And then this is another example of a module / brick. So this is that mid-level. And this was great, but like most lithium battery companies, they're out of business, so you can't buy this anymore. Luckily, Purdue had like $100,000 worth of them donated in 2014. So these have been powering probably 5 to 6 go-karts a year for the last 10 years. Old faithfuls. Every year, you know, EVC takes them apart and measures the health of each cell by determining internal resistance. We'll talk more about that later. But once again, so if this is a lithium ion brick module, and I told you it's a 1S 8P configuration, what's the nominal voltage across these terminals? 3.7 volts. What is most likely the max voltage across these terminals when it's fully charged? 4.2 volts. What is most likely the fully discharged voltage? 2.5. 2.5, 2.8. But don't forget when there's voltage sag existing. So in order to get to 2.8, you have to like trickle it down. So effectively, like when you get to 3 volts is really, you know, because of voltage sag, it'll go below 2.8. So, and what's neat is if you take this apart, don't pull too hard on that. You can see on this one, the, let's see, they have tab welds going to the copper bars. Yeah, tab welds going to the copper bars that put all of these terminals that are all in the same direction because they're all in parallel, right? So these only make one series cell. So all these are the negative terminals, all these are the positive terminals, and these copper bars bring all of the terminals up to right here. So I love, this is a great brick. And the best thing about this brick is when you were talking about assembling a pack, they just fit perfectly in line and the terminals pretty much touch and you just compress them together. So when I get shown a battery pack for evGrand Prix and I'm supposed to decide is this a safe battery pack, you know, we want to decide, were you the one doing these tab welds as a student or were they professionally done? Because, you know, those are pretty important and you want them professionally done. So if someone said that they were building with a brick like this, I'm like, great, you're probably not going to screw up a compression fitting and leave, well, you could leave it loose, which gets things hot, but most likely your compression fittings will be fine and your pack's going to be fine. But there are a lot of teams that want to start with a cell and make a highly custom battery pack. We've made the definition of highly custom battery pack when you start with an individual cell. And if you started with these individual cells, see right here, you got the positive terminal, you got the negative terminal. Then now you have to do tab welds on each one of these. You get a nickel sheet and you tab weld on each one of these things. And then that sheet, the next half of that sheet goes to the negative terminals. And then then there's another sheet, well, there's a sheet down below, and then the sheet, and you kind of snake through the battery pack. And those tab welds can get screwed up. There's a lot of, and then you don't compress them all together. What's nice is when you stick these all together, there's also nice compression in the whole pack, so everything's tight. You know, when you electrically connect all these, you haven't talked at all about how you're mechanically fastening all these cells within the battery pack. So mechanically putting all your cells together and fastened. So I think we use the word statically rigid. Well, you would probably know the better terminology of all the components within the battery pack, and nothing is shaking inside the battery pack, because that is when bad things happen. So I'll pass this once again. 1S 8P. This is made by Boston Power. I think this guy is what, 60 amp hours technically. I can pull up the data sheet. We're gonna learn. We're gonna get really good at reading data sheet. Oh, it says right here, 3.65 volts, 42 amp hour. So if I take 42 divided by 8, I would get the amp hours of each individual cell, right? That's that bad boy around. Don't lick the terminals. All right. Sorry. There we go. Okay, a reminder that we are recording this as well, so that's why I'm going pretty quick, and this will be available later for you guys to review, because we're going to design a lot of battery packs. I'm sharing. Tell me if I'm not sharing my screen anymore. It's pretty important. All right, here we go. Let's get with it. So, battery pack design, at least the way that I do it, it's iterative. You got to start with something, right? There's tons of things that you can choose, and you have to start with something. So that's why I always define it or make it an iterative process, because you know I see all these constraints and I say, well, I have a motor controller and that was free because it's in the basement over here, so I'm going to use that. And given this motor controller, what are my options for battery pack voltage? What are my options? Well, that's usually the limit right there. But let's go through. All right. So I started taking notes here. I'm not going to read that word for word because we're going to talk about it as we do it. Let's make a hypothetical race situation. Actually, no, I'm sorry. This won't be hypothetical. Let's review evGrand Prix race. What is our max voltage? 100 volts. What is the max energy in a pack? You guys know it? 4.2 or 3? Can I remember? We'll say 4.3. I think it's 4.2. We'll do 4.2 kilowatt hours. You guys follow me on this? Actually, I'm sorry. I skipped a step. I'm not supposed to know these things. So we're going to go to the race website, and we're going to look at the rules. evgrandprix.org. I pulled the rules up already. We're going to get really good at reading data sheets. We're going to get really good at reading rules. So let's see. The evGrand Prix rules, only 38 pages. Only 38 pages. Those are changes. Here's a summary. We probably want section 6. Section 6. Okay. Power and energy monitoring. Power and energy limit. The peak limit cannot be above 14 kilowatts. Boom. So we have power limit. What else? Yeah, what's your question?
So like during the actual race, how do they make sure that teams don't go over that limit? Or like
The power and energy monitor that we install on the kart.
oh
Yeah, so that's why for anyone else watching this, evGrand Prix is an open race, meaning it's not a stock race. You can choose whatever chassis you want. You can choose whatever motor you want. You can choose whatever battery pack you want. Well, you have to design the battery pack. And the way that we make sure that it's a fair race is we stick this box on there called the PEM, the power and energy monitor, measures instantaneous voltage, instantaneous current, therefore calculates instantaneous power. And if it ever goes over 14 and it says as is average over 0.5 seconds, then you will, well, there's different ways that we apply penalties, but every year we usually have to disqualify at least one team. And the winner last year was significantly over in power. We think it was due to a mistake in the programming. See you guys back there. and the kart was overpowered for the entire race. So that wasn't just like a blip and then disqualified. That was like the whole race was over and they were disqualified. So, but we also, by the way, EV Grand Prix calculates energy used during the race, which means we calculate an energy per lap, a watt hours used per lap, and we actually give an award for the most efficient kart. They usually range between like 30, maybe down to 20 watt hours per lap, all the way up to like 120, 150 watt hours per lap. So that's kind of neat that we have those aspects of the race. So we know the power limit's 14 kilowatts. Powertrain, sidebars, tires, power and energy limits. Where's the energy? No. Okay, you want to do? I'm gonna search kWh. Nope. All right, I'm gonna type kilowatt dash hour. Okay. Cool. Energy. Control F is your best friend. That's confusing. Power energy limit. There it is. 4.32 watt hours. Lovely. So our energy limit in EV Grand Prix is 4.32 kilowatt hours. I'm trying to think if there's anything else we need. There's kind of an assumption you need to realize. Well, are we going to make this pack with the full amount of energy? What if EV Grand Prix allowed 8 kilowatt hours? But this is a 50 lap race, so I guess there's some givens we need to figure out. Here are your rules. How about some given? Given is 50 lap race, 0.26 miles per lap. All right. And oh, thanks. 0.26 miles per lap. Well, let's keep going. We're gonna design a battery pack for this, guys. I think that's about it. All right, where do we start? Where do we start for making this battery pack design? Oh, yeah.
I'll try and put together the total distance and then find that with some knowledge of the amount of energy you might spend per lap.
Like figuring out how much energy you need, because you're trying to figure out how much energy you need to finish. So, yes, there's two things that you can do here. You could just make the maximum energy allowed, like get near 4.3. But then again, if you don't know anything about this race, that could be way too much and your battery pack is too expensive and too heavy to be competitive. This is not an endurance race. This is a race about speed. Your pack can be too heavy and you won't be competitive. So what I would do in reality, because you really don't know, like you'd have to go test to determine a watt hours per lap. Because I just told you it's about 60 watt hours per lap. But if you're coming into this, if you're a school from England and you want to compete in EV Grand Prix, you don't know that. You could do your own test. How about you go out and do your own test and you determine 50 watt hours per lap? And that's one way to scientifically do it. Realistically, guys, what I would do is I would call a team that's already raced in this and say like, hey, like what size battery packs roughly are in this? And they're like, oh yeah, it's usually about 3 to 4 kilowatt hours. So just find someone that's done this before. Rachel?
You also look at the old PEM data.
Yeah, I do supply PEM data from over the years, and it shows how much energy was used. It shows like current over time, and you can see it, which would be amp hours used, and you convert to kilowatt hours used. So basically, let's just make the assumption that we're going to use 60 watt hours per lap. What does that mean? So that means what? How many watt hours are we going to need to finish this race? 3,000, which actually is really convenient. Therefore, 3 kilowatt hours will be necessary to finish the race.
Where'd you get the 60 watt hours per lap? Is that just from Prix?
That's a given. That is me with experience telling you that 60 watt hours is something that your kart may do.
What if this was like completely from scratch? Then would you like maybe look at others?
Yeah, actually, I mean, this is part of your design problem. We're actually doing what your final is in this class. And you're going to have to do that and make a decision on watt hours per lap. Um, Basically, but the assumption for the final, a lot of people use evGrand Prix as a baseline. And then if the vehicle's heavier, I basically say justify your watt hours per lap. If it's heavier, it's higher. If it's a longer lap, it's higher. So I basically say just justify your watt hours per lap and then go from there. So this is kind of like a given. That's why I'm putting it in the given section. So did you guys realize that 60 times 50 is 3 kilowatt hours and that's necessary to finish the race? Someone tell me I'm wrong. You can't finish the race like this. Why can't I finish the race like this? Can you close the door if you don't mind? You can't finish the race like this. I've said it a million times. Voltage sag. The bottom 30% of your state of charge is unusable for definitely for racing, but it's also unusable for like going on the highway if you're a consumer. Okay, because if you're sitting there, where's my voltage curve? If you're sitting, I mean, like if you're sitting right here near the end and you're determining if you have to get to 0% to finish the race, when you pull current from the battery pack, it will sag. And near the end here, it sags below the 2.8, or I guess this is like 2.8 is where I would cut this off. And your battery pack, your BMS will kick in and shut your cart off, or do limp mode, as we'll talk about later in the class. But anyway, so we all agree the bottom 30%, I say 30, just as a rough estimate, of your battery pack is unusable. So let's increase this battery pack by 30% to finish. All right, so 3 times 1.3. Yeah, 3.9. Okay, so weight, need 30% extra energy to be competitive at the end of the race. So let's go with 3.9 kilowatt hours. You like it? It actually worked out really well. I didn't plan for that. Now I know you can finish this race with about 3, so 60 watt hours per lap is being generous. Good.
Do you know roughly how much extra weight going to the max capacity would have?
Part of this design is going to talk about weight.
Oh,
So yeah, we'll get there. So we know this is the energy we want. So we've gone somewhere, but we also need to still make important decisions in order to continue with this iterative design process. What should we make an assumption of? Let's say you were given a motor controller. And let's find a motor controller. Let's say it's the Curtis 1236 motor controller. I like to use Electric Motorsport. Well, yeah, maybe showing my age by saying 1236, because I think that's an old model. Electric Motorsport. So if you weren't given a motor controller, I would just say your next step here is deciding your motor controller. So you can approach this through either way. So brushless motor controllers, like Sevcon and Curtis are very popular. Sevcon, well, there's an important difference. Sevcon, if you are bold and you want to be competitive, Sevcon gives you a huge advantage because in Sevcon programming, you can choose a power to limit to. You can literally say, limit this to 14 kilowatts. That's amazing. Because what happens is in Curtis, you have to limit with a current. Meaning, if what did we say? If we do an 82 volt battery pack and we're limited to 14 kilowatts divided by 82, you're limited to 170 amps. And actually, you need to do it at the max voltage. So we'll say like 90 volts. At the beginning of the race, if you pull 155 amps, you are going to be multiplied times your 90 voltage, and that's going to be your 14 kilowatt hours. So you have to limit to 155 amps. But what happens is we know at the end of the race, if the pack voltage is roughly 84, let's say at the end of the race, your pack is actually like 78 volts. Well, now you can do 180 amps in order to stay under that limit, right? But you've already programmed your cart to 155 amps. So your effective power decreases, the power that you can create decreases as your pack voltage decreases, and you can't reprogram your limit. So that's where it's very strategic to go with SevCon. Now, you probably ask what are the downsides of going with SevCon, and every year I warn people, SevCon is very, very, very difficult to get working. Even just the software on your freaking computer that you have to pay a bunch of money for is really hard to get working. And then it's just like everything about it. It's very custom. No one's real. I mean, it's gonna be hard to find someone to help you. Maybe there's enough knowledge on campus these days to get your cart working. But I mean, the cart that I coached and advised last year that they made, they chose SevCon because it seems like they want, you want to be competitive, you choose SevCon, and they were on the side of the track. They didn't even get any practice laps in. Like the first times they raced was the actual race. They finished, so that was great, but they just couldn't get the cart to go the proper speed. Like just all the settings are very, very complex. Rachel, would you guys agree?
Yeah.
Yeah, but would you still buy SevCon?
We have an internal debate over whether we should or should not.
Oh, you're having this debate right now.
Yeah, because there are some people that are just fed up with trying to get it to work and not getting it to work, but then other people that are like, well, if we spend time when it's not right before the race working on it, it is doable.
It should work, yeah.
We should be able to.
And you guys got burned in the opposite direction. It's not like you guys didn't race. You raced, got first, and then had to be disqualified because your programming of the cart didn't go through or whatever mistake happened.
Well, I'm not entirely sure what happened.
Yeah.
In the programming, it said it was limited to like 12 kilowatt hours, something like that. Like,
Yeah.
It said it in the program, and like we opened the program back up to see if like it hadn't saved, and it like came back to the same power limit.
Oh yeah. So that's the classic SevCon issue is like you think you've done it, but it's not actually working. And it's no fault of SevCon. It's a very complex parameters in multiple different locations, right? So there may have been a parameter in another location that wasn't changed. So anyway, so Curtis, I guess you could they make brushless DC Curtises, but most of the time you're going to use a Curtis with an AC9 induction motor. And those are, I mean, evGrand Prix has been won plenty of times with Curtis and AC9 induction motors. And I mean, Curtis has a lot of programming capability, but most likely the day you hook it up will be the day that it will run. You're not going to spend a week trying to get it working. So anyway, for this sake, let's just go with Curtis. There's a 1232 one, 48 volt. Don't forget, this says 48 volt. Is that nominal or is that maximum? Right? So that's the question. You get to click into it to decide. I'm guessing that's, I don't know. Actually, I don't know what it is. What do you think it is? Because this is where the max voltage is very important of a motor controller. You don't want to go over it. It'll throw an error if you go over it. I don't really care about this one. We'll find one that we may use and I'll look into it. 48 volt, 600 amps. Here's a 48 to 80 volt, 550. This is probably overkill because 80 times 550 is way over 14. 550 amps times 80 volts. This can do 44 kilowatts right here. Now, it's overkill, but it's kind of fun because when you're not racing evGrand Prix, you can really show off. But then your battery will be limited, right? So there's always something in the powertrain that will limit you. But this is a pretty beefy guy. But it's still overpowered for what we need. This guy can go up to 144 volts, 500 amps. This is a good, what's 48 volt? Interesting. Let's see if this one can go up to a higher voltage. Maybe this is one we want to consider. Oh, I don't know. That's weird. Usually they have a lot more data sheets. So, brushless internal permanent magnet. Oh, that's motors. Shoot. Let's find, you know what? Let's just go with SevCon. We're not actually programming this thing. So, I'm going to go back to controllers, brushless controllers. We'll go with SevCon. And 36 or 48. This is 72 to 80 at 180 amps. 180 times 80 volts times 180. This at its peak will go just barely the limit. So I would say this is a little too small, probably, for what you want. You want to go over 180 amps. This is 300 amps, 110 volts, but can this go as low as 50 volts? Like you want to think of like this motor controller will be around for a while. It'll probably be paired with multiple battery packs. So you want a very versatile, motor controller that can be used with a 48 nominal pack up to like an 80 volt nominal pack. But don't forget, 48 volt nominal pack goes down to like 36 volts, and an 80 volt nominal pack goes up to like, let's say 100 volts. So you want the ideal motor controller will be between 36 volt and 100 operating for the sake of evGrand Prix. Let's see if we can find one of those. This one probably doesn't go all the way up to 100. This one could work for us based on its power capabilities, but it probably doesn't go as low as we want it. Maybe it does. That's a beefier version of the one I said. So let's go back to the one I said. Let's see what the actual limits are of this motor controller. Sevcon Gen 4, there's a ton of them out there. They're all Gen 4. S4 is the amount of current, meaning it's about 350. This can do both sine cosine encoding and UVW encoding. That's how it tracks the rotor in the motor. Good.
Is that voltage, like what it's rated for? Like why does it go for that?
The electronics within it are limited. So that's why motor controllers are meant, but like we're gonna see what the real what the real limits are. Here we go. Operating voltage 39 to 116. Let's do it. This is a great controller. You can use it. What is a 20S pack? 20 series cells times the lowest voltage of 2.8. Maybe not 20, 14 series. Let's do a 14 series pack. A 14 series pack, like if you see a pack with these cells, they're all 14 series. 14 series times 2.8 is 39 volts. This is perfect. This is like meant to be used with all the way down to a 14 series pack. I say 14 series because 14 series nominal, 14 times 3.7 is 51.8. So 14 series is the closest you're going to get to a 48 volt pack. Right? We don't work in steps of 12 with lithium. So a 14 series pack is very similar to a 48 volt pack. So they can go all the way down. And then the max you can kind of do in evGrand Prix is a 24S pack. 24 times the max voltage of a cell of like 4.2 is 100.8. Technically, that's kind of over. Hopefully, maybe the cell's actually like 4.18. So, but we'll say that's allowed. Let's say that you can go up to a 24 series cells, lithium cells in evGrand Prix to stay under that 100 volt max. Well, yeah, you can get away with that here. So you can use from 14 series cells up to 24 series cells pack with this motor controller. Did you guys follow me on that? Great. And you had to look at the actual operating voltage. So anyway, we found our motor controller. Let's use it. All right. So motor controller, Sevcon Gen 4, 39 volt to 116 volt, 350 amp. Yeah, about it. We like it. We know that we already did the conclusion that this controller can work with a 14S pack up to a 24S pack. It can actually do more than a 24S pack, but 24S is the max for evGrand Prix. Plus. Any questions on that so far? We have our motor controller. Now we need to design the battery pack. I told you this class was battery pack design. We haven't started talking about the battery pack yet. I guess this was a powertrain design. We are going back to these guys. All right. Anyone want to guess what our next step is for what do? We need a battery pack to race this kart. And by the way, the motor, there's motors out there. Just get one that can do 14 peak, right? So you probably get away with like an 8 continuous. I already talked about that in another class. 8 kilowatt continuous will probably be fine with a 14 peak limit. Like you don't need to get a 14 continuous motor. It's probably too heavy, too overkill. You're not doing 14 continuous in this race. That's a 14 peak. Okay, so anyways, that's why I'm not spending much time on the motor. It is BLDC though. Where do we start with the battery pack?
Cell type, like cell chemistry.
Yeah. Okay. I mean, honestly, there's so many places to start. There's no right answer. How bold are you? Do you want to start with the cell level? Do you want to make a highly custom pack? I don't recommend it. EBC's done it. You guys have done really good, but it's probably very long hours. So let's go with my recommendation. Well, if you can find brick/modules, that's awesome. There's not, I mean, if you find a brick/module, they're usually not great. Let's see if I can just find some real quick. Lithium battery module. I mean, nowadays there may be some, and you can test them.
There's some that we found that are really nice.
Yeah, I mean, if someone's done the research for you, and let's say like don't forget they're all 1S, and let's say we want 40 amp hour. So that's much bigger than what we're going on there. But these discharge cables are kind of small. Like I wouldn't trust, like, once again, what's great about this tablet is that these that have the little cables, you're limited by the cables that they install. At the same time, that's not great battery pack design to have a million of these freaking, discharge cables all around, right? You want something like this with actual terminals that like take the current directly into the next cell. So you're more talking like things like this. I recognize this, and you don't want to buy that battery. Lithium iron phosphate, and those would actually maybe be considered prismatic cells. What, Rachel, do you know the name of the one that you were saying?
They're called lithium block, jet modules, and evolve electronics.
From what electronics?
Evolve electronics.
Oh, Evolve. Yeah, they make or they sell the Orion. Right?
Yeah, they do. They're the official distributor.
Of Orion BMSs. Everyone uses Orion BMSs. Good.
They ship it like 2 days.
Yeah.
BMS 2 days later.
If you're telling me Evolve sells this, maybe I'll like it. Evolve battery module. They spell Evolve weird. Right? This is a pouch cell. Probably lipo.
T-Mobile.
Go to their website.
Yeah, what's their website?
EVOLVE electronics. Let me see what's full.
So, okay, what we're doing now is sourcing the lithium cell you're going to use. So this actually is something you want to do, spend a good amount of time on. There we go. Evolve Electrics. Evolve Electrics. Confusing. So here is, now that is what I'm talking about. That looks good. I mean, that looks obviously similar to what I showed you here. I'm confident that, there's decent compression and tab welds, and you can obviously form this together. And they already have the threaded compression fittings for you. And oh, by the way, they give you this nice guide to get, this must not be 1S because it has all these cell tabs. You know what I mean? Yeah, well, 10E. No, it is 1S. Okay. Well, I don't know why they give you all the cell tabs right there, because you can see them coming up, but they're all connected anyway through the high current discharge. So we'll just leave it. But yeah, I don't know what those are about. And you, by the way, you know what's great about this block? Double purpose. It keeps you from shorting. This is an important little do to keep you from touching that to that. So this looks great. This is a great design. Once again, I don't know why you would ever need to get to the terminals of each cell, but because if they're in parallel, they're already electrically connected, right? Nice job, guys. You found this?
In terms of looking at each cell, something that we noticed with the Boston packs, they have a fun mechanical issue since it's connected at the top and the bars go down.
Yeah.
As the pack wiggles, the bar can actually snap off some of the cells. And we had to go through and check each cell before to
Yeah.
see if something is loose in that drawings.
Yeah, like this bar right here comes off the cell. So maybe it's just a redundancy to the actual cell rather than the discharge bar.
Yeah.
The discharge bus bar. So this is phenomenal. Now obviously I mean, they even give you small increments because a lot of times you get 10 or you get nothing. You get 10, 5 or nothing. But the fact they give you 9, 8, 7, 6 gives you so much ability. Because you guys remember when I told you in battery pack design, I was like, what if you wanted a little more energy? And I said, well, commonly you'll add to the series cells, but it may take you out of range of your motor controller. I said it's best to add to the parallel cells if you want to add more energy to your battery pack, but it's almost impossible to like just add one cell. So the fact that they actually increment by one parallel in each module, this is gold, man. Are we going to see a kart this year with these?
Like,
They cost so much money.
Oh, do they?
it's a 550.
Well, that's for a discount.
I-
Well, we'll talk about costs here, here at the end. But anyway, I guess in order to continue with this design, I guess I was taking down the path of what I advise. Like if you were actually making a battery pack, I would have definitely advised using this. But we're going down the path of what if you're making this for the company you work for and you're going to produce 1,000 of them a year, 1,000 of them a month, you cannot pay a middleman. You have to make a highly custom pack. Okay. So that was my fault for taking you down the path of talking about modules. You have to make, for our design, we're going to make them with lithium, with individual cells. So let's get back to our design. And let's say this. Well, you guys can choose lithium iron phosphate. You can choose 18650. You can choose 21700s. How about we go 21700s? They're very popular. 18650s are kind of old. You guys want to do that? All right. Like I said, at some point you just got to decide. So 18650 battery store is more meant for like single battery purchases from like people who vape. But they do have a good selection. I don't know, maybe you could buy enough. They're just kind of expensive for buying a lot. Oh, do they? You guys have you bought from them?
Yeah,
I like the
it's a
stuff
really good discount.
because they show so many cells, right? And these are 18650. I mean, I guess let's say I'm not gonna limit us to 21700 yet. This is where we decide, and this is where I need to add to here. Well, I said choose your parallel series configuration. We know our series configuration. I'm gonna say note, parallel config may have to wait until after you decide on which cell you will use. So you can't really use parallel configuration yet. Decide on a battery cell. Take into account if you want a power dense cell or an energy dense cell. All right, so that's what we're going to look at. And we're definitely only going to get through one design today. But let's look here. And I'll just tell you, the higher, and I know 18650s based on their amp hours, right? The amp hours of 18650s range from 2 amp hours to like 3.6 amp hours. Okay. You've got the amp hour capacity, and then you've got the amp discharge capability. You can convert this into C rates immediately. You take 10 divided by 3.45, right? And that's just interesting, but we'll just stay in the world of amps since that's what they use, okay? The higher the amp hour capacity, the more energy dense it is, obviously. And you give up, just chemically, this is how batteries are produced. They're either produced to have a lot of energy or they're produced to have a lot of power, meaning C rating. So this one is definitely one that has higher amp hour, higher energy or capacity, and lower discharge. This is an energy dense cell. This is a power dense cell. This can do 25 amps and only has 2.8 amp hours. This is a medium tier one. This is one that kind of balances both. This is high energy, low discharge. So this is an energy dense. This is middle of the pack once again. By the way, should I talk about, I say 10 amps. That's confusing. 10 amps continuous, 10 amps in peak. I don't know. Let's find out. Let's look into it. 10 amps is your continuous. Does it give me a peak? Not right here. You can go into the data sheet, but confirmed. So here's your nominal voltage, 3.6. I say 3.7. Sometimes it's 3.65. Here's your max voltage, and here's your cutoff voltage, meaning the BMS will cut you off. So that's 2.5. And by the way, this is a great cell. I recognize Panasonic NCR is a really good cell. This is an energy dense one. Now we're in the data sheet. We're in the data sheet. Let's confirm what we saw right there. Rated capacity, 3.19 amp hours if you discharge. Well, this is assuming 0.67 amps of discharge. So that is not very high discharge. This is like using this cell to do something like electronics, slow discharge. And you get that much capacity. And that is, I guess, if you charge it all the way up. But they also give it to you if you don't charge it all the way up, because it damages the cell if you charge it all the way. Typical. They give you the temperature. You have a little more capacity if the temperature is a little higher, meaning when it's colder, you get less capacity. We all know that. So you see that right here in the data sheet. And you also want to go to graphs. This is just information from a graph that you can see down below. Nominal voltage, 3.6, we know that. End voltage. Here's your discharge or charging current. Don't charge at more than 1.657 amps. We want to see discharge. Continuous discharge, 10 amps. Internal resistance should be around 38 milliohms. Here's your weight. The weight's important because that's how we're going to determine the total weight of the battery pack, which was your question. Operating temperature. So it doesn't really give you a peak discharge, but I want to take this one step farther. Oh, cycles. 300 repeated charge and discharge cycles will get you to usually it says like it'll be down to like 80% state of health. But anyway, let's keep moving. Standard charge method. Let's just keep moving. I want to show you the graphs. The graphs are important. Come on, give me some graphs. Oh man. No graphs in this data sheet. They just gave us a table. Darn. Okay, well, I'll show you that later. But I can tell you right now, I know this will not be the ideal battery, but I want to choose it so that you can see the same thing. Okay. This is more of an energy dense battery. Let's use it though. Let's use it in our math. We only have 20 minutes left, so let's get moving. 3.45 amp hours, 10 amps continuous. Yep. Yeah. All right. We're going to use, and this is where it's iterative. You will iterate using another cell. And I'm going to tell you for sure, we're going to have to, because this cell is too energy dense. So iteration 1, let's use this cell. It is 3.45 amp hour, 10 amp continuous. Boom. All right. We know that it's the regular normal lithium ion, normal 18650 lithium ion. So zooming back to where we are, did we decide on a series configuration? Do we know the motor controller can do any? So what series configuration do we want to do? I mean, this is where the motor may be more specific. Commonly, you can go 14 are very common, 20 is very common. Actually, here's one. Here's a decide. Let's decide series config. Here's a big one. Big consideration. If you stay at or below 16 series cells, then you can use the less expensive Orion Junior BMS. Anything over 16 series cells requires the normal Orion BMS. So more series cells equals more expensive BMS. So you guys have to like, these are all considerations. So I don't know. You guys want to go 16? Sound good? Series cells 16S. What does that mean? What's our nominal voltage? I'm going to trust you. Oh no, the pack now. It actually, this says 3.6 nominal. So 16 times 3.6, 57.6 is your nominal voltage. Max voltage? Let's use 4.2. 67.2 volts, and we'll use 2.5 for min voltage. Or I guess, I like the term cutoff. We really need to start using that. Cutoff voltage. What is it? 2.5 times 16? 40 volts. You got it? So we know the battery pack voltages. It's huge. That's a big step. We decided how much energy we need to do. So we did this early on, which was nice. So how do I get to my amp hours from here? This is part of that battery pack characterization. How do I use this to get to the amp hours that I need in my pack? For my already determined 3.9 kilowatt hours. Come on, guys. P equals IV. So P being power slash you can throw the hour on there. So 3.9, 3,900 divided by V voltage will give you your I amp hour. So we'll use the average slash nominal voltage. So we'll do 3,900 divided by 57.6. You guys agree with that? Yeah. So 67 amp hours is what we like. And if you're building to the actual limit, be careful about your rounding because it's 67.7. If I go up, you may go over the limit if you're designing to the actual limit. So I'll just say 67 amp hours needed. All right. How many parallel cells? Come on. What cell did we use?
Divide your amp hours by the amp hours of each individual.
I like it. So 67 amp hours of the pack divided by 3.45 amp hours per cell. So 19.4. I can't have 0.4 of a cell. Also, I really don't want an odd number because when you put these things together, I mean, I guess those packs you saw kind of went lengthwise, but like sometimes they're not exactly lengthwise, so you want them more like square. So I would recommend an even number. So I'd recommend we take the parallel from 19.4, which is what my math tells me, to 20. So 20 parallel. And we know that 3.9, I can do that because 4.3 is the limit. If I add 0.6 of a cell, I'll get more energy, but now I'll just be more like 4 kilowatt hours, right? So that's the perk of not actually designing to the limit. So 19.4 cells, we're gonna go with 20p config. You like it? And by the way, let's now correct ourselves. What's the amp hour of the pack? Therefore, amp hour of the pack is now 20 parallel cells times 20 parallel cells times amp hours per cell of 3.45. 69. Therefore, amp hour of the pack is now 69 amp hours. Okay. And the nominal energy of the pack is, and I guess maybe I can write the math here. Why don't we do that? 3.45 amp hours per cell times 20 cells equals. And then energy is 69 amp hours times 57 nominal here. The nominal energy of the pack is 69 amp hours times 57.6 nominal voltage equals 69 times 57.6. 3.974 kilowatt hours. You like it? This takes practice, which is why we're going to do a lot of these. We've talked about energy. We've made the pack that will finish the race. We know it'll finish the race because we already did our math on 3.9 kilowatt hours finishing the race. Okay. But will we be competitive? I don't know. Let's find out. Now let's check power capability. 10. What's the max discharge of a cell? 10 amps. Remember that? You're just gonna have to know this. Parallel cells add discharge capability. I mean, that kind of makes sense, right? Either just memorize it or try to understand that it makes sense. Parallel cells add discharge capability. Therefore, 10 amps per cell times how many parallel cells? And don't forget, parallel. When you're talking amps, you'll always be parallel. Times 20 cells equals 200 amps. I should clarify continuous. Max continuous discharge of a cell, 10 amps. Parallel cells add discharge capability, therefore 10 amps per cell times 20 cells, 200 amps pack continuous discharge. What is our power now? And just for simplicity, let's just use nominal power or nominal voltage, right? So what numbers do I add? Do I match? Yeah, nominal voltage 57.6 nominal volts times that amperage, right? What do we got? 11, we'll say 11.52 kilowatts. This is below our 14 kilowatt limit. Now that said, this is continuous. We kind of need to know the peak capability. And let's dig a little harder because I'm a little mad that this thing hasn't told us a peak. We really need that. Continuous discharge current max. 3, 4, and 6. We'll look at 3, 4, and 6. Discharge at high rate or high temperature environment will accelerate the degradation of the battery capacity as state of health goes down. We also want to look at 4. The maximum discharge current is for a single cell. However, after the battery pack assembly, maximum discharge current will be limited by protection current or device. Yeah, BMS, obviously. And then 6, maximum cell surface temperature. Okay, so here's my conclusion, guys. This is an energy cell. It's not meant to go higher than 10 amps. I mean, if we're sticking to the data sheet, this in no way says you can go over 10. I mean, it says continuous, but then it says max. So according to the data sheet, this is not supposed to go over 10 amps. So for that reason, I'm out. Shark Tank? No. I'm out of this cell. So just reread cell data sheet and concluded 10 amps is the absolute max peak discharge.
Is that for the individual cell?
Yeah, but here's individual cell, but then we multiply times 20 cells.
So you're saying because the data sheet says 10 amps max continuous, we can't go over that. Yeah,
If we're sticking with true design, I mean, like it'll do it. It'll degrade the battery faster. Now you are in a racing scenario. Designing for racing is a much different thing than trying to design for consumer products. So like actually, like yeah, if I don't know if I'd approve it, but if you put this on a track for evGrand Prix, it'd probably be fine. Good.
oh, sorry. So what was like other specs for like batteries? They say something like
We're gonna iterate again.
210
Yeah.
amps.
We're gonna iterate again, and maybe we'll choose one that is too powerful. And then we'll get the three little bears. We'll get right in the middle. So, by the way, side note, we have some energy capability. We could add more parallel cells and maybe get to our 14. Now, I mean, we could actually do it proportionally. Let's do it proportionally. I can proportionally make this 4.3 minus 3.974. I can add 0.36 kilowatt hours to this. And that's an increase of 3.974. I can make the pack 8% larger. So because I could show you in math why it all works out. But I can increase the power by 8% if I put them all in parallel. So I'm going to increase that 11.53 kilowatts times 1.08. I can get to 12.45 if I go all the way up to 4.3 kilowatt hours by adding more parallel cells. There is a point at which you have enough parallel cells where you can hit 14 kilowatts. Do you guys understand that? Because you're adding more. Yeah, anyway, you understand that. So, but now you've gone over the energy, and that's a classic problem with lithium iron phosphate. Lithium iron phosphate is not powerful. Well, the old stuff, new lithium iron phosphate is pretty good. The old lithium iron phosphate, we could not run in an evGrand Prix situation because of this exact issue. Like you do the math and they couldn't produce enough power. Like, okay, well, let's put another one in parallel. Well, now you're well over the 4.3 kilowatt hours. So it was kind of like a catch-22, and which is why evGrand Prix rules are that way, so that you got to get the right balance. Plus, you just have to use energy. This is just a bad design. Like, if you only realistically need 3 to 3.5 kilowatt hours to finish the race, and you design a pack with 6 kilowatt hours, this is bad design, right? I mean, yeah, you can be competitive with the 14 kilowatts, but then in this whole process, guys, you're going to realize, and I with the final, the way I stipulate it is like, you need to end up with, I think how I phrase it, a good design. Like the situation where I just said you made your battery pack super heavy or super large compared to the needed amount. It's just a bad design. Yeah, you may have satisfied all constraints technically, like it passed tech, but you won't be competitive because it's too much weight, or it's going to be too expensive, right? Like you got all your constraints, but these are out of whack, and therefore it's bad design. So, good.
So are we trying to hit that max 14 kilowatt limit? Because what is thankful that technically like you're kind of more efficient.
I would actually be faster because 14. I would actually love to see that raised. And when you're not racing in evGrand Prix or practicing, you're going to be showing your hometown. You're going to be showing your friends in the safe, hopefully a safe environment. But you want it to go 20. Like Top Kart is a company, and they've built a kart, and that thing that holds the record on the track here. Well, they hold the record because they pulled like 30 kilowatts. So like I would design the 20 kilowatts at least. Kilowatt
And then
hours.
just limit it in software.
Yeah, and then just limit it in software in the motor controller. So well, real quickly, let's see. We cannot use this cell. Iterate again. All right. Iteration 2. All right. So I know we got to go here soon. Let's just real quickly do the power cell. This guy. 2800, 25 amp hour capability. Well, I guess I should add it. So it's Sony. Yeah, there it is. Normal 18650 lithium ion. It's 2.8 amp hours, 25 amps. Let's actually keep. We're going to keep our a lot of what we had. So keep pack voltage and required. Well, you have to do parallel again. Keep pack voltage, which is what did we said? It was 16 series cells. We said it is right here. All right. So where do we go from here? Let's go back to our 3.9. Previously determined we need 3.9 kilowatt hours. So how many parallel? I guess we already did the math on that. It was roughly oh no, it's new math. So it would be right. P equals I times V. It's 3,900 divided by nominal pack voltage, 57.6 volts, right, guys? Equals, oh, this is, so the amp hour is the same. It's the same as before. 69 amp hours. Okay. Now we're going to do 69 amp hours divided by, we said 2.8 amp hours per cell. And that's where the math changes. 69 divided by 2.8. So now we're going to go 24.6. We'll round up to 25. Round up to 25 parallel cells. 25P. Pack is 16S 25P. And let's see if that works. And actually, I should have been clear on iteration 1. This pack was how many P? 20P. I guess we need to say with this specific cell. Cool. Let's see if that works. Well, we know the energy is fine because we just designed it to, I guess you could do the math, but it's roughly 69 amp hours. Check power capability. We're going to know here in a second. I'll let you guys go. Technically, this is 1015, right?
Yeah.
Okay. Check power capability. P equals IV again, right? So I is roughly 69 amp hours. We probably should figure out what it actually is. 25 parallel cells times 2.8. Oh, it's 70. Okay. 70 amp hour pack, right? Times, we're going to do nominal voltage of the pack. So times 57.6. That doesn't seem right. Oh, no, that's energy. I just did the energy. Sorry, guys. We're trying to do, yep, well, it's 4.032 kilowatt hours, but that's not what we're trying to figure out. Check energy. Why didn't anyone stop me? Check power capability. What is the amps per cell? Come on, what are the amps per cell? 25. Where it is? It was right here. 25 amps per cell times 25 cells equals, what is that, 625? 625 amps, right? pack capability. We don't know if that's continuous or not, but we'll just play along. All right. So now, what is that? 625 amps times 57.6 volts equals 625 times 57.6. 36 kilowatt capability. And heck, that may even be continuous. Yeah, that's continuous. The peak could be even more. So this is where, and remember I said like technically this pack would work. And that's why I got to be clear in your final project. I want to tell you that like I will not accept when this is so out of whack. Like you don't need to use this high cell. And the downside, here's the downside. Here's the downside. Where's it? Much more than you need. Downside is that you use too many cells. Pack is too expensive. What is that? 16 times 25. It's 400 cells. 400 cells. And I guess maybe you're gonna have to wait till next class for iteration 3. What do you guys think? You guys dying to know? Well, you can do the math on your own if you want, but I could have told you just because I've done this a million times. The best battery for this particular application is the middle of the tier, 3 amp hour, 15 amps, right? Obviously that's the one in the middle. But here's the trick, guys. And this is what we're going to continue to do. This whole premise was based on our race rules of evGrand Prix. We're going to change that. I actually pulled up Formula SAE's rules. And, or we can make like a golf cart type application. So we're going to iterate this again with different applications of different rules, more energy, more long distance versus this is kind of like a sprint. So anyway, good class.
Excuse me. I had a quick question on the homework.